Okay, let's take a look at this problem. First of all, notice that there is nothing attached to the piston, or the piston here. So what they're trying to tell you is that that's going to be a constant pressure. In the previous problem, there was an arm or something that was attached to indicate that somebody could be pushing it. That's why the pressure changed over there. But anyway, in this case, and they also tell you that the pressure inside the cylinder is constant. But anyway, so you can see that from the diagram as well. Okay, so here they give us the mass, they give us the two temperatures. They have an electrical current which is putting energy in. It's in the form of electrical energy, and they tell us that the pressure. They also tell us the heat transfer, which is probably the hardest thing to determine. But anyway, they tell us that. And what they want to know is how much electrical energy is applied. Okay, so give it some thought. Pause it and give it some thought. Okay, so here all I'm doing is writing down what we're given and doing a few unit conversions. First of all, it's an ideal gas. I know the mass, I have the two temperatures. I'm going to convert them into absolute temperatures because I'm going to use the gas formulas. I'm given the pressure. Notice that the pressure is given in kilopascals, and since I want to use standard units, I'm going to convert that into pascals. That way it's newtons per square meter. And then the Q, I do the same thing. The Q is given as kilojoules. I want to convert it to the standard unit. So that would be 60,000 joules. Remember, a joule is a Newton meter. Okay, so give some thought to what you're going to do with this. Okay, so what I'm going to do is I'm going to account for the energy that's in the air. So on my left-hand side, I have energy that's being put in by the electrical circuit. I don't know how much that is, so I'll call that WE. And then what I've got is some expansion, and because the pressure is constant, the work is equal to the pressure times the change in volumes. I'm doing it for the entire system, not per kilogram, so I multiply by the mass in front. I'm going to pause it and draw a PV diagram for you. Okay, so in red, I've drawn the pressure and volume. The work of expansion is always the area under the PV diagram, and because P is constant, all it is a rectangle, and that's why I'm just trying to show you why the expansion work is P times V minus P times V. That's all I'm trying to show you. Anyway, so now you've got the energy equation. Over here on the right-hand side, this term is for an ideal gas. That comes out of the chapter notes. The internal energy is the CV. The enthalpy of a gas is CP, and this is internal energy, and so that's why I'm using CV. Okay, so if you notice, I counted three unknowns, the W and the two volumes. So now think about what you're going to do, and pause the video. Okay, so what I did was I wrote two red equations here. They're basically the ideal gas law. P times little v equals RT. I'm going to write it for the first point, first temperature, first pressures, and also for the second point. So now if you look at it, I've got three equations, the black and the two reds, and I've got three unknowns. So now I can go ahead and just solve for it. So pause the video and you solve for it, and I'll show you the answers in a minute. Okay, so here in blue, I've solved the two red equations for the two volumes, and the unit on this is the standard unit. So this would be cubic meters per kilogram. So make sure that you've got those two. Pause the video now and go in and calculate your work. Okay, so here is the work that I calculated from the top black equation using the volumes. So the question is, why is this number different than the answer that was given. Well, if you notice, look at the units on the answer. They're kilowatt hours. And what are the units on the W that I calculated? Well, these guys are joules. Why? I have trouble with this zoom. Okay, so these are joules. Oh, shoot. I'm going to pause till I get this fixed. Okay, so anyway, these are joules. The reason they're joules is because I'm using the standard units, and so the energy is always going to be newtons times meters, which is a joule. Okay, they want watts, kilowatt hours. So there's a unit conversion that a watt is equal to a joule per second. So in red, then I'm just going to convert this. So first of all, I convert the joules into kilojoules by dividing by 1,000. So I get 843.9. Okay, and then a watt or a kilowatt would be a kilowatt second is a kilojoule, and so then you have kilowatt seconds, and then you just convert the seconds into hours. So what you're doing basically is taking 843.9, dividing by 1,000, and then dividing by 3,600. And that gets you the number 0.234, which is the value given. Okay, so that's the end of that one.